4 plus the cube root of an. So what does that mean for us? Let's just write that down. A1, meaning the first term in the sequence is 1. And the nth plus 1 term, which is dependent on the nth term, it's equal to 4 plus the cube root of an. So come on, let's get it. Use mathematical induction to prove that an is between 1 and 8 for all n is a set of positive integer. So first we start by proving that a1 is true. All right, so you can write for n is equal to 1. When n is equal to 1, we have that a1 is equal to 1. All right, and since a1 is equal to 1, it implies that a1 is between 1 and 8. a1 is between 1 and 8, and so therefore a1 is true. So therefore n equal 1 is true. Since n is equal to 1 is true, what do we need to do next? What we need to do next now is assume n equal k is true. So for n equal k, for n is equal to k, right? For n is equal to k, we're going to have that a k, all right? We're going to have a k is between 1 and 8. And remember, this is an assumption. All right, this is an assumption. So we assume that n equal k is true. So assume n equal k is true. Okay, good. Now we need to show that it is true for n equal k plus 1. Now this is how we're going to do it. There are many ways you can do it, but I'm going to start with ak is between 1 and 8, right? So if ak is between 1 and 8, ak is between 1 and 8, then what that means is if I were to cube root all the sides, then if I were to cube root all the sides, the cube root of ak, if I were to cube root it, the cube root of 8 is 2, and the cube root of 1 is 1. Nice. Now if I were to add 4 to both sides now, so I would get 4 plus the cube root of ak, the cube root of ak, all right? I would get that adding 4 to both sides. Adding 4 to the right hand side would give me 6. Adding 4 to the left hand side would give me 4 plus 1 is 5. All right, just wanted to make sure. But guys, remember that 4 plus the cube root of ak is ak plus 1. So what this is telling me then is ak plus 1, ak plus 1 is between, ak plus 1 is between 5 and 6. But guys, look. But 5 is greater than or equal to 1, and 6 is less than or equal to 8, don't it? Yeah, man. So what that tell me then is that ak plus 1 must be between 1 and 8. So ak plus 1 must be between 1 and 8. Nice and easy. So now you can say hence n equal k plus 1 is true. So you can write hence, let's put that here, hence n equal k plus 1 is true. All right, so then now with induction you always write a conclusion. So your conclusion now is hence by mathematical induction. Hence, by mathematical induction, the statement is always true for all natural numbers of n. All right, the statement up here, so this is always true. Nice and easy. That takes care of the induction question. Soft. So that is part A of question 3. Now let's look to know part B. Let's look at part B. What is part B saying? Part B says that let k be greater than 0. All right, let k be greater than 0. Now, since k is greater than 0, all right, let k be greater than 0, and let f of k be equal to 1 over k squared. All right, let k be greater than 0, and f of k is equal to 1 over k squared. And let's hear what they're asking us to do now. They said that show that f of k minus f of k plus 1 is equal to that thing there. So let's do that. F of k minus f of k plus 1. F of k minus f of k plus 1. Now, f of k minus f of k plus 1. F of k is equal to 1 over k squared. Minus f of k plus 1, you replace k with k plus 1. So you get 1 over k plus 1 all squared. So you get 1 over k plus 1 all squared. Nice. So you have 1 over k squared minus 1 over k plus 1 all squared. Okay, now if you go ahead now and you expand the denominator for that side, you're going to get 1 over k squared minus 1 over k plus 1 all squared. When you expand that, it's going to become first term squared plus twice the product of the two, which is plus 2k, plus second term squared, which is plus 1. After you do that, so now you have k squared and k squared plus 2k plus 1. All right. Well, it didn't even need to expand it. Based on what I'm seeing down there, we didn't need to expand it. So let's not expand it. I thought they wanted us to expand it. It didn't have to. Looking at the question, it just found the LCM. So all we need to do is find the LCM. The LCM between the two is going to be k squared times k plus 1 all squared. And then k squared into this, leave k plus 1 all squared. Minus k plus 1 all squared into this leaves k squared. Now k plus 1 all squared minus k squared. Remember, k plus 1 all squared is k squared plus 2k plus 1. And so when you subtract the k squares, you're going to just get 2k plus 1 in the numerator. So in the numerator, you're just going to get 2k plus 1 over your k squared times k plus 1 all squared. This was a very boring question. You can even yawn. Oh, too easy. This was boring. All right, no little spice to it. No spice at all. No sugar, nothing. All right. So that's the first part of the question, that f of k minus f of k plus 1 is that. Generally, when you take the difference of two terms, you know that a method of difference question is coming. It is coming. I don't know when, but it is coming. Now, part B, it was coming in part B. Part B says, hence, find the sum from 1 to n of 1 over k squared minus 1 over 1 plus over 1 over k plus 1 all squared. So we're finding the sum. Really and truly what we're finding is the sum from 1 to n of f of k. So we're finding the sum from 1 to k of f of k minus f of k plus 1. That's what really and truly finding. All right, this is what we're finding. Now, once you're doing this, you're finding the sum from 1 to n of f of k minus f of k plus 1. It's going to be equal to, now, I'm going to work out the sum from 1 to n of f of k first. The sum from 1 to n of f of k, let's put it in blue. When you put in 1, when n is equal to 1, 1 square is 1, plus, remember sum means adding. When k equal 2, you get 1 over 2 square, which is 1 over 4, plus, when k equal 3, you get 1 over 9, and you continue to when you put in n, and n is going to be plus 1 over n squared. Cool. Minus, let's do it in a different color now. Let's do this in purple. Let's say minus, let's f of k plus 1 now. When k equal 1, you get 1 over 1 plus 1 square is 1 over 4. So you get minus 1 over 4. Then put in k equal 2. 2 plus 1 is 3. 3 square is 9. So you get a quarter plus 1 over 9. Plus, you keep on plugging in values until you reach the last term. When you put in the last term is, when you put k as n, you get 1 over n plus 1 all squared. Nice. So that's method of differences. Now, look here. Now, a quarter minus a quarter, this quarter gonna cancel. This 1 over 9 gonna cancel. All the other terms gonna cancel. This 1 over n squared gonna cancel with the 1 over n squared before here. And so what you're left back with is 1 minus 1 over n plus 1 all squared. Nice and easy, soft. You're left back with 1 over 1 minus 1 over n plus 1 all squared. That's part B. Nice and easy, soft. It says now, hence or otherwise, prove that the sum from 1 to infinity is 1. It says hence or otherwise, so you don't have to use the hence. But I'm going to use the hence, okay? Because the sum, they're asking us to evaluate the sum from k equal 1 to infinity. They're asking us to evaluate the sum from k equal 1 to infinity of 2k plus 1 over k times k plus 1 all squared. But the only little, here we use the word little, the only little trick is that the sum from 1 to infinity of this, we have to realize that this is just the sum from 1 to infinity of f of k minus f of k plus 1. That's the only little trick. So this is just the sum from 1 to infinity of f of k minus f of k plus 1. That's the only little trick. But remember, the sum from 1 to infinity of f of k minus the sum from 1 to infinity of f of k plus 1. All of this we had just evaluated, and we found that it is equal to 1. So all you're really asking us for, remember that all of this now, we're just finding the sum from 1 to infinity. So this is going to be 1 minus 1 over, you're going to plug in n as infinity now. Plugging in n as infinity, you're going to get infinity plus 1, infinity plus 1. We're replacing it with n now. We're replacing n with infinity. But no, infinity plus 1 all square is infinity. 1 over infinity is 0. And so the sum works out to be 1 minus 0. And 1 minus 0 is 1. So hence, the summation of this is 1. Too easy. Soft. Then we go to part C. Part C says, obtain the first 4 non-zero terms of the Taylor series expansion of cosine of x. Obtain the first 4 non-zero terms. So before I can actually do that, I just want to write down the Taylor series formula. So just to remind us of the Taylor series formula. The Taylor series formula tells us that f of x is equal to f of a plus f of a plus f prime of a times x minus a plus f double prime of a. Just writing down the Taylor series formula, f double prime of a times x minus a square over 2, and it continues. This is just the Taylor series formula. Don't you ever forget it. Okay, now that we're done write down the Taylor series formula, it wants us to use the function f of x as cos x, and we're gonna write it in ascending powers of x minus pi by 4. So in this case, they're telling us a is pi by 4 and x is, and f of x is cos x. Let me change the color and do that in red. So in this case, f of x is cosine x. So f of x is equal to cos x. So if f of x is cos x, then what does that tell us? That tells us that f of pi by 4, f of pi by 4 is going to be equal to, plug in x as pi by 4. The cos of pi by 4 is the cos of 45, and the cos of 45 degrees is root 2 over 2. Nice. Then now, if f of x is cos x, then f prime of x is going to be equal to, when you differentiate cos, you get minus sine. You differentiate cos, you get minus sine. And so f prime of pi by 4, f prime of pi by 4, f prime of pi by 4 is actually going to be equal to, plugging in x as pi by 4, and we're getting minus root 2 over 2. Okay. All right, and then now we differentiate this now again to get f double prime of x. When you differentiate it again now, when you differentiate sine, you get cos, so it's going to become minus cos x. And so what we're getting now is that f double prime of pi by 4, f double prime of pi by 4 is going to be equal to minus root 2 over 2 minus root 2 over 2. And finally, just to finish it off right here, we're going to get that f triple prime of x is when you differentiate minus cos, you get sine. So you're going to get sine x. And we already know what f, so f triple prime, I'm going to write f3 of x, which means f triple prime of x. F triple prime of x is equal to, again, root 2 over 2. Okay, good now. So now we can go ahead and proceed to say that f of x, now we can proceed to say that f of x is equal to f of a is root 2 over 2 plus f prime of a, which was minus root 2 over 2. So instead of putting plus, I'm going to put a minus here. So this is now minus root 2 over 2 times x minus a. And a in this case is pi by 4, so it's minus x minus pi by 4. Then it is now plus f double prime of a. F double prime is minus root 2 over 2 again. So this becomes minus root 2 over 2 times x minus pi by 4 square. And all of this is being divided by 2. All right. And then we have plus f triple prime, which is root 2 over 2. Now we have plus root 2 over 2 times x minus pi by 4 cube and this is divided by 3 factorial, and 3 factorial is 6. Now guys, I really don't like how this look with so much fraction. Root 2 over 2 divided by 2, root 2 over 2 divided by 2. I'm just gonna rewrite this a different way. I'm gonna pretty this up a little bit. So when you're dividing this by 2, root 2 over 2, you can actually pretty this up a bit, and I can't bother rewrite over a whole line. So please bear with me. I'm gonna take away this 2, take away this line, and rewrite this as root 2 over 4. Right? I really can't bother write over another line. And I'm gonna take away this, write this as root 2 over 12. Root 2 over 2 divided by 6 is 12. So I rewrite it that way. All right, that looks easier to understand. Okay, so that's the first part. That's 5 marks. Now let's say hence, calculate an approximation of the cosine of pi by 16. So part 2. So this is cos x. All right. So this is a formula for cosine x. All right. And so what that means is the cosine of pi by 16 means that we're going to substitute x as pi by 16 in this formula. So the cosine of pi by 16 is going to be root 2 over 2 minus root 2 over 2 times the cos, well, times pi by 16 minus pi by 4, pi over 16 minus pi over 4. All we're doing is substituting x as pi by 16 minus root 2 over 2 minus root 2 over 4, sorry, minus root 2 over 4 times x minus pi by 4, and x is pi by 16, so this is pi by 16. This is now pi by 16 minus pi by 4 all square plus root 2 over 12 times x is now pi by 16 minus pi by 4 cube. All right, so you put all of this in a calculator, and then you're going to get your value for the cosine of pi by 16. So I'm going to put this in my calculator. I'll write it out one by one so you can see how I get each term. Root 2 over 2 is 0.707. So the first part is 0.707 minus, put in this part now of the calculator, root 2 over 2, root 2 divided by 2 multiplied by pi divided by 16 minus pi divided by 4 multiplied by minus root 2 over 2. I get plus, so this part going to work out to be plus 0.4165. Then I work out the next part now, which is pi divided by 16 minus pi divided by 4. Then I square that result and multiply it by root 2 divided by 4. And that's giving me minus 0.12267 plus, finally, I have pi divided by 16 minus pi divided by 4. I'm going to cube that result and multiply it by root of 2 divided by 12. And I'm getting minus 0.02408. All right, so now I put all of this in my calculator, and I'm going to add them up now. 0.707 plus 0.4165 minus 0.12267 minus 0.02408, and I get 0.977. All right, and that's my answer to 3 significant figures, 0.977. So that's the cost of pi by 16. If you don't believe it, put in the cost of pi by 16 otherwise. You're going to get 0.98. So our answer is relatively accurate. So I guess we rounded off pretty fine. And that's Taylor series expansion. Soft. Let's go to question 4. Question 4 says, obtain the binomial expansion of the quart root of 1 plus x plus the quart root of 1 minus x. So let's do this binomial expansion. We want the quart root of 1 plus x plus the quart root of 1 minus x. Okay, this is what we want. Now that this is what we want, we're good. All right, so we want this now. I'm going to rewrite all of this. This is how we're going to do it. We're going to rewrite all of this as 1 plus x to the quarter power. This is how we're going to rewrite it. 1 plus x to the quarter power plus 1 minus x to the quarter power. That's how we're going to rewrite it. But do you remember binomial theory? Well, if you don't remember binomial theory, let's jog your memory a little bit. Binomial theory, if we can remember correctly, it tells us that 1 plus x raised to the nth power, 1 plus x raised to the n is equal to 1 plus nx plus n times n minus 1 x squared over 2, and it continues. All right, this is known as the extension to binomial theory. You remember that? Yeah, man. And this we're going to use and tackle this easy question. So let's tackle this easy question using binomial theory. So using binomial theory, the first part, 1 plus x to the quarter, or n is quarter. So overall, this is going to be equal to 1 plus nx. I said expand it up to x squared, so we can stop right there. So it's 1 plus nx, which is now a quarter, times x, plus n, which is a quarter, times n minus 1. N minus 1 is going to be a quarter minus 1, and a quarter minus 1 is minus 3 over 4. Just to check it, I'm going to put it in my calculator. I know it's sad, but don't laugh at me. A quarter minus 1 is minus 3/4. Just making sure. X squared over 2. So that takes care of this part. That takes care of 1 plus x to the quarter. Then we're going to need plus 1 plus nx. In this case, n is a quarter and x is minus x. That's going to be plus a quarter of minus x plus a quarter of, it's now plus a quarter of n times n minus 1. N minus 1 is minus 3/4 times x squared, which is minus x squared over 2. Okay, nice. So come we stay, so boom, and work this out. 1 plus 1 is 2. A quarter x plus minus a quarter x cancel. And then what is this simplifying to be? A quarter times minus 3 over 4 divided by 2. This is minus 3 over 32. And you're going to get minus 3 over 32 here as well. So you're going to get 2 times that, which is minus 3 over 16. So this and this, those two adding together to give us minus 3 over 16 x squared. All right. All right, so that's the answer. All of this, it just works out to be 2 minus 3 over 16 x squared. You see how much beautiful? Look at this complicated thing. All of it just going to be equal to 2 minus 3 over 16 x squared. Math is so beautiful. Nice. Now it says, by letting x equal 1 over 16, find out what is the value of the square root of 17 plus the square root of 15. All right, so get that. And we want to put x as 1 over 16. So let's put x as 1 over 16. So let's write that. Let x be equal to 1 over 16. If x is equal to 1 over 16, then what we're going to get is, on the left-hand side, we're going to be finding the square root of 1 plus 1 over 16. 1 plus 1 over 16 is 17 over 16. All right. Plus the square root of 1 minus 1 over 16 is 15 over 16. All right. And then this is going to be equal to, put in x as 1 over 16 here. So you get 2 minus 3 over 16 times 1 over 16 squared. So when you put all of this in your calculator, what you're going to be getting is 2 minus 3 over 16 times 1 over 16 squared. And I get 1.99999. So I get 1.9993. All right. Now, let me make some space and finish it up here. Let's make some space here. We're going to finish it off in here. All right, so we're going to finish it off in here. Now look what I'm going to do now. Now right here, so we have the square root of 17 over 16. The square root of 17 over 16 can be written as the square root of 17 over the square root of 4. Over the square root of 16, sorry. All I did was separate it. Instead of having it as the square root of 17 over 16, it's just the square root of 17 over the square root of 16. Plus, we can do the same for here. We can break it up as the square root of 15 over the square root of 16. And then the square root of 16, you just put right here. And that's equal to 1.993. Now, what is the square root of 16? I know it's embarrassing to say this again, but once again, put it in a calculator. The square root of 16. The square root of 16 is 2. This works out to be 2. So now we're getting that the square root of 17, and it's now over 2, plus square root of 15 over 2 is equal to 1.9993. All we have to do now is multiply through by 2. When you multiply through by 2, you're going to get the square root of 17 plus the square root of 15, take the square root of 17 plus the square root of 15. When you do that now, you multiply 2 by 2, you get 2 times 1.9993. You get 3.99 is the answer. I like to write it to 3 sig fig, but you can write it to more if you want. 3.99, you can even write the other 9. So I get 3.99 is the answer to 3 significant figures. Soft. Test it. Test and find out what is the quart root of 17 plus the quart root of 15. Yes, we're right. So we get the same thing. So that takes care of part A, soft. Part B. Part B says using, it says show that the coefficient of x to the fifth in the product of x plus 2 to the fifth times x minus 2 to the fourth is 96. Now there are two ways you can do this. If you know Pascal triangle, there's no issue in doing this. But if you don't know Pascal triangle, we're going to use combinations. So this is x plus 2 to the fifth times x minus 2 to the fourth power. I want to show the coefficient of x to the fifth power. So to find the coefficient of x to the fifth power, it's going to be two ways you can do it. Let's do it both ways. Method one. Method one, you could actually expand out everything and find out which one is going to give you your coefficient to the fifth power, or you can say it's going to be the term in x multiplied by x to the fourth term here, plus your term in x here multiplied by your x to the fourth term in here. Those are the two ways you can do it, all right? All right, but I'm going to go with method one. We're going to expand out all of this. So to expand out all of this, you're going to say x plus 2 to the fifth using combinations. It's going to be, when you choose 0 first, so 5 choose 0. So I'm expanding this part first. It's 5 choose 0 times x to the fifth plus 5. Wait, I missed out something. It's times 2 to the 0. You don't want to leave out nothing. You don't want them penalize you for anything. Plus, it's going to be 5 choose 1 times x to the 4, 2 to the 1, plus 5 choose 2 times x cubed times 2 square plus 5 choose 3 x square times 2 cube plus 5 choose 4 times x times 2 to the 4 plus 5 choose 5 times no x to the 0 times 2 to the fifth. Now this is going to be the expansion of x plus 2 to the fifth. All right, so this is expansion of 2 to the fifth. Now all of this is going to be multiplied by the expansion of x minus 2 to the fourth power. All right, expansion of x times x minus 2 to the fourth power is 4, because now n is 4. It's 4 choose 0 of x to the 4 times minus 2 to the 0 plus 4 choose 1 times x cubed times minus 2 to the first power plus 4 choose 2 times x square times minus 2 square. And I know you're probably saying, sir, why are you doing this long method? I want you to understand what we're doing first before I show you the short method. 4 choose 3 of x cubed times minus 2 to the first power. This is cube. This should be to the 1. Sorry. Plus, finally, 4. Choose 4. X to the 0 times minus 2 to the 4th power. A lot of work. But we're pretty much done now. So all of this is going to be equal to, you just put all of this in a calculator. This is now x to the 5th plus 5 choose 1. I believe that's 5. Put that in a calculator. 5 choose 1. That's 5. But then you multiply it by 2. That's 10. This is going to be 10x to the 4. So it's x to the 5th plus 10x to the 4. 5 choose 2. 5 choose 2, I believe that's 10. Then you multiply that by 2 squared. And I get 40. So I'm getting plus 40x cubed. Plus 5 choose 3 is 10 again. 10 times 2 cubed. 2 cubed is 8. So that's 80x squared. 80x squared. Plus 5 choose 4. 5 choose 4 is 5. And 5 times 2 to the 4. 2 to the 4th power. I know it sounds sad. 2 to the 4th power. That's 80. It sounds sad to be using calculator for that. It's 80x plus 5 choose 2. 5 choose 5. 5 choose 5 is 1. That's just 2 to the 5th. 2 to the 5th is, I don't need calculator for that one. I know that's 32. So all of that is now being multiplied by 4 choose 0 is 1. X to the 4. This works out to be x to the 4. 4 choose 1 is 4. Times minus 2, that's minus 4. Times minus 2 is minus 8. That's minus 8x cubed. Then 4 choose 2 is 4 choose 2. All right, put it in a calculator. 4 choose 2 is 6. And 6 times minus 2 squared. Minus 2 squared is 4. 4 times 6 is 24. So I didn't need a calculator for that one. That's 24x squared. Then you have 4 choose 3. Oh God, 4 choose 3. I can't believe I can't remember these out of my head. 4 choose 3 is 4. 4 times minus 2 cubed is minus 32. This is minus 32x. Then I definitely know 4 choose 4 is 1. Minus 2 to the 4 is 16. And they want the coefficient of x to the 5. Now look how we're going to find the coefficient of x to the 5. All right. Now to find the coefficient of x to the 5, guys, it is simple. Let me put it in red. It's going to be x to the 4 is going to, when you multiply x to the 4 times 80x, that's going to give us coefficient. That's going to be able to give us 1. All right. You have all of this, guys. We're not going to sit and expand all of this. But what I'm saying is when you multiply x to the 4 times 80x, that's going to give us something in x to the 5th. All right. So this one will give us, for coefficient of x to the 5, I'm going to write C for coefficient of x to the 5th. For the coefficient of x to the 5th, 80x times x to the 4, that's 80x to the 5. Then What else we're going to need to multiply? We're going to need to multiply 80x squared times minus 8x cubed. That's going to also give us something, 8x to the fifth. So 80 times 8 is 80 times minus 8 is minus, that looks like minus 640. So you get minus 640 x to the fifth. Then what else we're going to need? We're also going to need to multiply this 40x cubed by something x squared. So 40 times 24 is going to give us 960 x to the fifth. Right. I'm going to change the color now because I really want us to keep following. Now we're going to multiply this x to the 4. It's going to need to multiply by something x right here. So when we multiply those two, we're going to get 10 times minus 32. I don't need my calculator for that. I know that is negative 320 x to the fifth. Then we're going to need to multiply this x to the fifth term by the constant, which is 16. So we get plus 16x to the fifth. All right. So now when you add up all of these now, I'm positive you're going to get 96. Let's check it. 80 minus 640 plus 960 minus 320 plus 16. Yep. I get 96x to the fifth. So I get 96x to the fifth. Hence, the coefficient of x is 96. So you can say hence the coefficient of x is 96. Now I know I said I was going to do it the other way from the start, but being that it's so long, I want you to just check out the video on binomial expansion. Look at the examples that we do, and you're going to see us using that method doing other examples, and you'll follow there. All right, so this is just method 1 to do this. Okay, next part of the question. It says, use the IVT to prove that x cubed minus 25 has a root on the interval 2 to 3. All right, so use IVT to do that. All right. Use IVT. So first thing, I'm not going to write it as x cubed. I'm going to write it as x cubed is equal to 25. And so I'm going to subtract 25 from both sides to get x cubed minus 25 is equal to 0. And then I'm going to call this function g of x. I'm going to call it g of x. Didn't want to say f because everybody going to use f. I like when my paper is different. So g of x. Now the next thing you need to do is tell them that, well, g of 2 is equal to, plug in 2 here, you're going to get 2 cubed, which is 8. 8 minus 25 is minus 17, which is less than 0. And then g of 3 is going to be equal to 3 cubed, which is 27. 27 minus 25 is 2, which is greater than 0. Aha, so good. So now we can tell them, say yes. By IVT, we're good. So now we can write our conclusion that, so we can tell them first and foremost, g of x is a continuous function on the interval 2, 3, and g of 2 is less than 0 and g of 3 is greater than 0, and so hence by IVT, which means intermediate value theorem, hence by IVT there exists a C, which is an element of the interval 2, 3, such that g of C is equal to 0. Hence, there exists a root on the interval 2, 3. All right, so that's IVT for you. Soft. Hence, there's a root on that interval. Now it says the procedure used, they use A as 2 and B as 3, and it wants us to find an nth iteration. From the table, we're going to do this, and we're going to find the approximated root. So let's put up our table now. This is so easy. We're doing bisection method here. So we put up our table for part 2. All right. So up here was n. Then you have A. Then you have B. Then you have Pn. I'm gonna put P of n. Okay, I'm gonna put B of n. I'm gonna put A of n. Then right here, it is, I'm gonna call it Fp of n. Okay. N was 1, 2, 3, 4, 5, 6. Going down. And AN, they gave us that was 2, 2.5, 2.75, 2.875, then B end was, for B end we had 3, 3, 3, 3. For PN we had 2.5, 2.75, 2.875, 2.9375. Then we need f of Pn minus 9.375 minus 4.2031 minus 1.2363 and 0.3474. Okay, nice. So this is what we have now. Okay, all right. It says complete the table to obtain an approximation of the root of the equation x cubed equal 25. All right. So all they did now was, if you notice, when it is 2 and they use 3, the midpoint of 2 and 3 is b. So this Pn represents midpoint. Then they work out what is f of Pn. So what they do is they put in 2.5 in this function. So if you put in 2.5, you're going to get 2.5 cubed minus 25. That's how they get this value. So they do the same all the way here now. And so since they get 0.34 right here, when the midpoint is this is positive. We don't want it to be positive, all right? So how much more they want us to do it? We just need to repeat it 2 more times, all right? Now, the root is not between 2.875 and 3. So now we're going to use 2.93. We're going to use now 2.93 and 3. So AN is now 2.93, 2.9375, and BN is, well, since it's positive, we're not using 2.93, my mistake. Oh, how did those go away? Oh boy. How do we get this back? Control Z. Okay. All right, we're good now. Control Z, take my time. All right, good. So what we're saying now is that the root is going to be between 2.87 and 2.9375. So this is going to become 2.875, and over here is 2.9375. The midpoint of that is 2.875 plus 2.9375 divided by 2 is 2.90625. Then you put that in the function up there for g. So that answer cube minus 25 is negative 0.45, negative 0.45297. Okay, good. Now that we have this now, we need to do it one more time. So this is the 5th one. Let's do it one more time now for the 6th one. So for the 6th one, all right, since it's minus, then we're going to keep this BN value. And so right here now, this becomes 2.90625. That's now AN. BN is going to be your same, 2.9375. Then PN is the midpoint of those two. So you add them, 2.90625 plus 2.9375 divided by 2, which is 2.921875. And then you find f of Pn. You put that up here. So you get answer cube minus 25. You get minus 0.0549. All right. And so almost get the answer. Remember, you get the root when this is equal to 0. When f of Pn is 0, that's when you get the root. Since we get another negative here, we're going to put an we're going to change it again now to 2.921875. Bn remains the same as 2.9375. Then we take the midpoint of those two, 2.921875 plus 2.9375 divided by 2, and the midpoint is 2.92685. Then f of Pn is the answer cube minus 25, and we're getting 0.1457. All right. Now, of these two, which one is closer? Of these two, which one is closer? This is closer. This is closer to 0. This one is closer to 0. So what does that mean? Since this one is closer to 0, we can take this as an approximated root. So we're going to take that as an approximated root. And so an approximation of the root is 2.921875. Nice and easy. That's an approximation of the root. Soft. Now in reality, the root would be the cube root of 25. And the cube root of 25 is 2.924. That's the cube root of 25. But this is a good approximation. All right? Because I just wanted us to complete the table. So that's it. The approximated root is 2.921875. That takes care of module 2. So we're going to go on now to module 3.